and black holes. So they correspond to this sort of very broad way to classify the regular solutions that are here, that are there in this theory. These conical defects are in some sense new sort of regular solutions which didn't exist in the SL2R theory. And it's so the reason, okay, let me just explain what these are, and then I'll explain the name. So the reason for this sort of broad classification is that if we are looking at the Euclidean theory, and we have, let's say, we compactify the time direction as well. So as I discussed in the case of the BTZ black hole, when the time direction is compact, the boundary is a torus, which is parametrized by the sort of the phi direction and the t direction, and parametrized by parameter tau. So there are, it's a torus because there's the angular part and then there is the time part. So if you wish, in this language, so this is identified with this in this picture that I showed you. The boundary time circle is identified. And then, of course, there is the phi circle, which is here, which is also a circle. So there are these two directions on the boundary which are compact, which are circles. Now, two different things can happen when you go into the interior. So the first happens in ADS3. In ADS3, what happens is that this phi circle, smoothly sort of shrinks to 0. All right, this is in fact a picture of global ADS, and so the phi circle. So there are two things that can happen. In the interior, on the boundary you have a torus, but on the interior you can have the phi circle is contractible, and the example is global ADS, like this one. This phi direction as you go in the interior can be smoothly shrunk to 0, or the T circle is contractible, and example is the BTZ black hole. So you can have the time circle, and that is what the Gibbons-Hawking procedure uses, that the time circle as you go inside, so that's a little bit more difficult to draw. That's like the cigar type of this thing. The time circle is sort of shrinking smoothly to 0 in the interior, so one of these two circles, because the whole thing is topologically ADS type of these spacetimes are topologically trivial. You have one of these circles must contract, and you can have two distinct kind of geometries. So these are sort of purely topological characterizations, that the phi circle is contractible or the T circle is contractible, Now when we, so this is what will correspond to these solutions. So here, so we'll call these two solutions where so where the phi circle is contractible, we'll call them as sort of conical defect-like solutions, and black holes as the ones where the T circle is contractible. But when are these? So if they are contractible, if you want these solutions to be regular, then you will we need a condition like we described earlier about the holonomy, so this means that the spatial holonomy is trivial. That means the path ordered exponent of the gauge field, but along the phi circle. So this must belong to the center of gauge group. Where, so the argument is similar, namely that if this phi circle is contractible, then if I take the holonomy along this phi direction, along this circle, since it is contractible and since the theory is topological, there's no field strength. The holonomy here is the same as the holonomy of a small circle, and if it smoothly shrinks to 0 size, then this must be an element of the center of the gauge group. But if instead it is the other circle which is contractible, then we must have the condition like we had for the Gibbons-Hawking case, that we should demand that holonomy is trivial, and as I showed yesterday, as I described yesterday, that gives you the right periodicity of the temperature in the Gibbons-Hawking case. So that's a natural generalization along the time direction. This must be again a member of the center of the gauge group. So so the regularity, demanding regularity, so these are just the local solutions. This doesn't tell you whether the solution is regular in the interior. This is just so there can be many solutions which are not necessarily regular, demanding regularity is an additional criterion that you impose on these solutions, and that is in terms of the holonomy, because that is the so we don't have in ordinary general relativity we would say, oh, the metric, the curvature scalar should not blow up, and then you say the metric is regular, here we don't have that freedom, so we demand instead we don't have that intuition, because as I mentioned earlier, the gauge invariant observables are not just curvature scalars and so on. In fact, from the Chen-Simons point of view, there are very few gauge invariant observables, and holonomy is one of them. The field strengths vanish, so you can't build any non-trivial gauge invariant observables from the field strength. But the holonomy need not, gives you a constraint on the solution. So if you put in these values of the gauge field and ask for that they be trivial, you get the regular conditions. That gives you that gives you conditions on the A's, these functions L and W. So you can get generalized black holes this way, and these were constructed by Goodpearl, Krauss, and collaborators. You get new black holes, and then you can get these additional solutions which were not there in the SL2R gravity case, where the spatial holonomy is trivial. You get, in addition to global ADS, you can get other solutions which in some frame appear as if they have a conical singularity, but that's again a gauge artifact, because the conical singularity in terms of the metric appears as if there's a curvature, delta function of the curvature, but actually the fact that they are smooth, the holonomy, if you impose that the holonomy is spatial holonomy is trivial, you actually see that there are frames in which those are smooth. That conical singularity is a sort of a gauge artifact. So you have these two sets of novel solutions in these theories, which is something it's more in higher dimension. For instance, very few solutions are known of the classical Vasiliev equations. So 3 dimensions is an example where you can write out explicitly many of the classical solutions. Okay, so this is what I wanted to say about the SLNR theories. I'll just briefly generalize to the most general higher spin theories in 3 dimensions that you can consider. Any questions? So if you want to know more details about these solutions, etc., I refer you to those review articles that I mentioned in my first lecture. So, so the most general Vasiliev theory in three dimensions is not the SLNR class of theories. It's based on an infinite dimensional Lie algebra, which is called HS lambda. There's a parameter which you normally take to be a real parameter. So I'll define what this HS lambda is in a moment, because this Lie algebra is what generalizes to higher dimensional cases, well, at least specific, the contact with the higher dimensional cases comes from this general Lie algebra. It's an infinite dimensional Lie algebra, so unlike the SLN, so it's generically infinite dimensional. Lambda equal to n, when lambda equal to n, HS lambda sort of can be truncated to SLNR. So when lambda is an integer, a positive integer, then you get this SLNR. So it's generically an infinite dimensional algebra, but for special values, namely integers, it truncates to a finite dimensional SLNR. So the most general case, so this real parameter, actually without loss of generality, you can take it to be between 0 and infinity, and it's only at some specific discrete values that it becomes a finite dimensional SLNR. So the general Vasiliev theory is based on this Lie algebra, And it's given by there's still a Chern-Simons theory. And that means A, the gauge field, belongs now to this Lie algebra, HS lambda, and this contains all spins, at least all the bosonic spins, s equal to 2, 3 to infinity, except when lambda is an integer where it truncates. So in general, except when lambda is an integer, it contains all the spins from 2 to infinity. That's the generic case. And so what I told you was a very special case, but it's very illustrative special case. That's why, and it's more simple to understand. That's why I dwelt on this. So it's a Chern-Simons theory based on this. The equations of motion are still dA plus A wedge A, but now in this equal to 0. So equations of motion are these, etc. So the whole structure is very similar, except that the algebra in which it takes its values is now this much bigger algebra. And so let me just quickly give you a definition of what this HS lambda is. It's maybe a little unfamiliar, but if you sort of if you play with it a bit, it's not so formidable as it looks at first sight. So so once again, to construct this algebra, we start with JA which belong to SL2R, but now you consider sort of infinite dimensional representations of this JA, or well, to specify the Lie algebra, actually you can specify the Lie algebra in a completely algebraic way. So you start with SL2R generators and then construct all these dA1 to AS minus 1, so the construction parallels what I just wrote for the principal embedding. You construct these for all S equal to so you build these things, and so you consider all this. This is what is called the universal covering space of SL2, or universal covering Lie algebra of SL2R, and so that's this whole collection of these monomials. So you can do this for any Lie algebra. You can take the generators, you can construct products of the generators and define this universal Lie algebra, which is the union of this whole infinite set of generators. Obviously, they close amongst themselves, because when you take commutators of these using the commutation relations of SL2R, you will get back other monomials of this form. So this is what is called U of SL2R, but the HS lambda is not just that. You have to mod out by relations. The second Casimir, you mod out by the following relation, that the second Casimir of J is a multiple of the identity. So the second Casimir of J for SL2R is like the Casimir for so or if you wish, J0 square minus. So just like this, the angular momentum Casimir, this is just the SO2, 1 or SL2R Casimir. So you have all these monomials, but whenever you have this combination or this combination appearing, you set that equal to 1/4 of lambda square minus 1, where lambda is a parameter, just a real number. So you have all these, you consider all these monomials, but subject to this relation. And this thing is what is actually HS lambda. Actually, there's the identity piece in this which we remove, and the rest of it is what we call the HS lambda. And you can write down a convenient basis for this algebra, and you have that defines for you the general HS lambda. When lambda is equal to n, you can see that that's indeed the Casimir that you get for the n-dimensional representation, which satisfies, and then you can sort of truncate it because all the higher spins actually can will decouple. So this, but in general, for a general value of lambda, you can still define this. If you wish, this is a way to extend SLN to arbitrary integer, arbitrary real number. And so you can view this as a sort of a definition of SUN or SLN. You can do something similar for SUN, SUN for general integer. So it's a very nice, interesting kind of infinite dimensional Lie algebra, which you can construct. And so the general Vasiliev theory is based on this Lie algebra. So this, as I said, this A belongs to this, and just like so, it contains all these higher spin generators, so you have a sort of a huge theory with this big gauge symmetry, but many of the things that you sort of do for the SLN case sort of go over to the HS lambda case. But SLNR is simpler to introduce, that's why I focused on this. But once you get familiar with that, then this is just a further step. So you can also couple scalar fields. So I didn't talk about coupling matter fields to these higher spin theory, but you can couple, for instance, matter fields, and it's most easy to do in terms of this. So you can do it in terms of these HS lambda theories, and so you can couple matter fields. Examples, the simplest case, a scalar field, which we denote by C, which will also take values in this HS lambda plus identity. And its equations of motion are So to be consistent with the higher spin symmetry, its equations of motion at linearized level, the full nonlinear equations are more complicated, but at linearized level, it takes the following form: dc plus so this A and A tilde, so of course you had the A tilde as well, like we had in the SLNR case, there are the A and A tilde. So in some ways it's sort of in a bifundamental representation. It has a coupling to the gauge field, and the star product is essentially the product in this HS lambda. When you multiply two, you can define not just the commutator, but you can define a product also on the Lie algebra, because if I just take the product of any of these two, that's part of the Lie algebra as well. So so I can have, so this is the star product. There's the star product in the HS lambda. There's a product operation in the HS lambda. So in terms of that, you can define this, and then it tells you that the mass, so this actually, from this one learns that the mass is also fixed. It takes a very specific value in terms of this parameter lambda. So the matter field that you couple cannot be arbitrary. It has to have a specific value of the mass, which is -1 plus lambda square. So this is, and there are fermionic versions of this higher spin theory in which you can couple fermions as well, but I won't talk about that. So I didn't get to telling you about the dual CFTs at all in these lectures, but in a way that's okay, because though that's a whole subject in itself, but I'll just conclude by saying what the relation to this dual CFTs are. But since probably many of you haven't seen the ADS-CFT correspondence very much, I'll just be very brief. So we saw that this spin S, so these couple to the spin S gauge fields coupled to some kind of spin S currents on the boundary, so the general, let me go back to the SLNR. Vasiliev theory. So this corresponds to a 2D CFT with conserved currents of spin S equal to 2, 3, up to n. So you had this was the stress tensor, and then there was this W3, if I'm and in general you will have n functions. I wrote down here only the case with spin 3, but in general up to there'll be n-1 functions, which will correspond to conserved currents in the boundary theory, yeah. So these obey an algebra. These currents obey an algebra which is called the Wn